So up next we have George Zubelli. Of course, we all know and love George. And he's going to tell us about project evaluation under uncertainty. So, here's George, go ahead.
Okay, so, well, thank you very much, Sebastian. And it's really a pleasure to have you all here. But I must say that it's almost an impossible task to give a talk that is going to be judged in a fair way after the fantastic talk that Mateus gives. so anyway, I'll try my best, but it's unfair, Mateus. But I chose to be in that position. So the outline is basically the following. I'm going to give a small foreword. Then I'll give some background of why we are doing this, why do we care. I will mention some tools, but I'll really go very fast over that because these are tools that have, people here are very familiar with. Then I'll mention this algorithm that we use to attack the problem. It's called the hedged Monte Carlo algorithm. Mention some examples and draw some conclusions. So, but before I go on, let's do philosophy. I mean, it's kind of late. So I wanted to go back to the founding fathers. And I wanted to mention Fourier. It was a long quote. I kind of selected just the very beginning, but I suggest anyone who has a chance to take a look at the Théorie analytique de la chaleur. It's, well, it's there. It's basically saying that the study of, is the approfondi, the deep study of nature is the source or is the most fruitful source of mathematical discovery, and I hope you share these views, not only among ourselves, but with our more theoretical mathematicians. I mean, we all know who Fourier was and how important, how deep his work was. In the same book, there are also other quotes that are really joys and jewels, and they definitely should be read. Then talking about philosophy, I wanted to also mention another piece of literature that I learned it from the advisor of my advisor, who was Henry McKean. So Henry McKean told Alberto Grunbaum about this. It's about the unreasonable effectiveness of mathematics in the natural science. And here's Eugene Wigner when he was getting the Nobel Prize. So he argues in a very proper way that the ability of math to successfully predict events in natural science cannot be a coincidence, but must reflect some larger or deeper or simpler truth in both. So this is actually something philosophical, but I really think that this is something that we should learn from there. And I would even venture in a very, very speculative way to say that it's not only natural sciences, but also social sciences. And since we have been talking about finance as both a natural and a social science, so I think that it's interesting to have that. So more mundane things. I'd like to draw your attention, and perhaps I don't have the energy or didn't have the time to go deeper into these speculations. But I'd like to draw your attention to the talk I'm giving now and talks that happened earlier today and other days. In particular, Chris Rogers' talk on, in a certain sense, Monte Carlo simulations and subjects of that sort. Sebastian's talk also is deeply connected to the things I'm talking about. And I would venture to say that Cajo's talk on the three-fund separation theorem is connected to this. Okay. And I hope you join us tonight to discuss under some caipirinhas or with some caipirinhas why I say so. So this project came about as a result of some cooperation we had with industry, with Petrobras in particular. It was a project that has had at least 5 or 8 years. I would say it went on for about 8 years. And actually, I don't know if Fernando Ayub is still around, but oh, here he is. So I'd like to thank him for introducing us to this subject. So it's basically project evaluation. Some people call these real options, but for us it meant something that was actually a challenge, because real options is a very, very, let's say, well, it's subject to arguments. I remember Sebastian giving a talk many years ago about real options, and Ramakant going right at his neck, and Sebastian survived very well. I wouldn't have survived that well, but perhaps at least I wouldn't have survived at that point that well. Anyway, so the one thing we learned, that when you try to evaluate a project, and in commodity-related industries, but in industry in general, that we have complex claims. The claims, let's say, the actual things that you're going to evaluate are not simple at all. They are actually very complicated claims. They are usually barrier clauses. For example, an obvious one is that the company cannot go belly down or belly up or belly in any bad direction. Well, the other thing is there is a kind of exotic character to the evaluation, so that it's very path dependent. There is a presence of the cash flows and decision trees. So all these things make the claim evaluation, the project evaluation, very complicated. Optimal exercise times. I mean, nobody in the right mind would start, let's say, extremely cash demanding business in a place that's going with the economy bad. So all these things are very important in the decision. And there is, in many companies, especially in commodities, companies that have some trading desks, so there is a mix of historical and risk neutral measures, meaning that the trading desks would be probably trading things that are, or commodities or other equity that might be very, very much correlated to the type of project that the company is developing. So there is a mix between them, and in this sense we have to somehow do something about this. And there are lots of unhedgeable claims, like the weather, the oil production of a well, the political stabilities in a country, bad mood of politicians and other bad actions of politicians. In any way, in the so-called real option world, we are interested in assessing some kind of monetary value, such as to create a new firm, invest in a new project, start a research and development project, and to, for example, suspend operations under adverse conditions. So all these things make things very, very complicated. And the question is then how to evaluate projects and their optionalities under uncertainty in a consistent way with market fluctuations, especially if you have a kind of hedging available to you through some operation in the financial markets. Well, on real options, there has been a lot of research. The subject has been going on for a while, and I'd like to mention just a few papers, but obviously this is not an extensive list, a comprehensive list. It's just a small sample to tell you how long this has been going on. And in any case, just for people, especially students, who are not familiar with the subject, basically one of the key ingredients that one teaches to students in the very first classes on real options is the concept of a spanning asset. In other words, an asset that's highly correlated with the project value and somehow is going to be used to evaluate the project. So in a certain sense, the project would be evaluated, for example, by taking the soup over all stopping times, the optionality of starting this project, I must say, with an investment eye, with a value v is going to be evaluated by taking the sup over all stopping times between now and a capital T time. That is a time where you would not be able to invest anymore. And then you would consider models for V where this volatility would be estimated and the growth rate would be estimated with respect perhaps to some dividend model. So this is more or less the classical, model for real option evaluation. This leads to the Black-Scholes model with free boundary conditions. This per se is a very interesting mathematical topic, but this is somehow a little bit in the past because there are lots of criticisms concerning this model. In particular, there is a very strong criticism that's due to Hubalek and Schachmeier, and it concerns the limitations of no arbitrage arguments for real options. It basically hits exactly on the issue of the fact that the markets are not complete. And not being complete, there is a range of values, and with this range of values, you may be unable to price properly and find optimal stopping times in a proper way. So this I learned firsthand discussing with Schachmeier when I told him very excited, oh, I'm studying real options. He said, you should read a paper of mine. and then, of course, it's good to learn from the masters. So this is actually a very serious criticism. And that kept me and some collaborators, in particular, I'll cite them, but I would like to mention Max de Souza again. He has collaborated with me for many years on this subject. So what to do, how to handle such things. So anyway, we are going to present now a model which is related to the actual practical problem that came from the project we had with Petrobras, which is basically the following. We have some kind of oracle for cash flow generation. Such oracle for cash flow generation is what many companies have. And if you were here for Claudia's talk, she talked tremendously about something that was called PlanNAB. Well, we had something that was called PlanInv, I think. And it's some kind of big set of optimization routines that are put together, integrated in such a way that given all the prices and all the costs and all the different information that the company gathers would give as output after some optimization a corresponding cash flow. And this is done inside this black box. And it's done by taking traded assets, which are, for example, price of oil, gas, whatever, and non-traded assets, such as, for example, labor costs, or such as, for example, production flows in the wells, and so on, and would put together and generate some kind of cash flow. So from there, these cash flows, well, one can say, for example, that they are highly related to, independent on commodity prices. Then one can say that it's possible for financial hedging. And these cash flows are usually coming from differences when you are trying to evaluate a project by taking the value of the project, meaning the cash flow coming from the project and the cash flow coming from not having the project. So these things are usually obtained from difference, so these things can be positive and negative, but they are usually lower bounded, just for making things clear. And also, they, in many situations, would depend from differences between different commodities. So in that sense, the estimation of the process themselves would be subject to, would increase the error. So what I'm saying, for example, is think of a project where you get extra cash flow from the difference of a combination of gasoline price and oil price. For example, you're producing some special kind of refinery, and from the spread between the gasoline and the oil price, you could get some extra income. So this is the kind of thing that I'm talking about. You would have this type of extra difficulty in the calibration of the model. So these things are all coming from, as I said, some kind of cash flow producer. So that, I think, relates beautifully with what Chris was talking about, because he was mentioning that you had simulations. You had simulations of the assets. You had simulations of the options somehow. But you didn't have the full machine at your hand. And you could not cut it in pieces and say, OK, this is the function that I have, and I'm now going to use it as a pricing mechanism. Also, such oracles are adjusted to run with and without the project, as I said. So these are sometimes very time-consuming, and therefore, you don't have a huge number of evaluations. Usually, when people talk about Monte Carlo methods, even using very fancy algorithms, very fancy techniques, such as, for example, well, open your favorite book on Monte Carlo methods, important sampling, so on and so forth. These things are very time-consuming, and usually you're not going to have available to you 100,000 simulations or more. So you have to handle that. Then there are the window of opportunities related to that. So as I said, stopping times, complexities, and so on and so forth. So what I'm going to propose here and show you some results we obtained is actually a methodology that is simple, yet not too simple, and try to fulfill somehow those requirements. This paper that we published just a few years ago, well, I mean, submitted a few years ago. It was published recently at the Springer Fields Institute Communications. Actually gives the details, and that's part of my talk today. So, as I said, there are challenges. There is a historical measure issue. There are managerial views. There is market incompleteness. There are unhedgeable risks, and there are multiple assets. So everything that you would hate to see in a problem is there. I'd like to mention and give credit to other approaches. In particular, there is work of Jaimungao and Loshrin, and there is more recent work of Jaimungao and Collaborators. It's still in the very same issue, right? Am I wrong on that? Or is some?
I think so.
Yeah, I think it's there too. So anyway, it's quoted, it's cited in the paper, so you can certainly go and look there, or just Google Jaimungao and invest on Jaimungao if you follow the preceding strategies. Or Wikipedia. Sebastian, do you have a Wikipedia yet? No. We should go for Wikipedia. We should have a Wikipedia. Okay. So then, what do you do? Well, we take a kind of pedestrian approach. We use risk minimization one. It's something that people have been talking about for many years. In particular, we are inspired in the works of Potters, Bouchot, and Sestovic, but this has been around for a while, and I'm sure in versions that are much deeper than what I'm saying here, but I'm trying to keep it pedestrian, and so basically, what we did was to consider risk as something that's proportional to the variation of wealth balance. And so one would construct the price of the option or the derivative at a time t. We would like to use a hedging portfolio vector, and xt would be the price of the traded assets. And then what we'll do is the following. Look at what's happening at time t and what is going to happen at time t plus delta t, backward induction type of thing. So if you bring back to present value and look at the difference in these two portfolios, then the variance, meaning you take this difference square, you take the average over all possible scenarios, and you'd like to minimize this. So this is the intuitive idea. This leads to actually a very important minimization problem where you minimize both in phi and v. Well, that minimization in principle can be done, and it actually has a connection with something that is very well known in math finance. It's the idea of using the Fourier-Schweitzer decomposition. I'm going to actually, in the interest of time, skip very fast through this. Perhaps instead of even saying it, just show you the main slides. So this has been well known for a while. Filmer and Sheed, for example, is a reference for this. It's to use this minimum martingale measure, and that would be constructed by, for example, taking a portfolio where you have a numeraire or a cash kind of thing, and construct a portfolio. Then you look at a gain process, a cost process, and then you consider admissible strategies. So as I said, this is pretty well known. This I'm going to skip. I'm sorry about that, but you get at the end to using this methodology that, as I said, is very well known. The former Schweitzer result, where you would have hedging in complete markets and discrete time. This, by the way, has lots of extensions to continuous setups, in particular to BSDEs. I'd like to mention the work of Professor Karoui extensively, and also of other people on this subject, so I'm not going to go into that direction. What I'm saying here has an interpretation in the world of BSDEs, and in particular, there is even numerical results by Emmanuel Gobet and collaborators on this subject. So anyway, to make the long story short, what we are doing here is basically to price everything in this so-called risk minimum martingale measure. And in this minimum martingale measure, we, in fact, evaluate the projects. Now, how do we do this in practice? Well, we are dealing with American options. So we start from the simulation of the scenarios in the historical measure. We produce the cash flows. We combine this construction with the Longstaff methodology, or equivalently, we apply the Bouchot-Potter-Sestovic hedge Monte Carlo method. And in order to do that, we decompose the condition expectation in a basis that's generated by functions of xt. Now, to be precise, I'm going to just take a few minutes to describe you the algorithm that we use. So we initialize the project value. We initialize the payoff function for all the scenarios that are available, and these scenarios are going to be produced by this machine, this oracle that I was talking about. Now, backwards, we would go and define in the basis the composition of these functions and compute backwards the components of such functions in this, so as to solve this problem in an appropriate way. Connecting actually also with the work that Timo has mentioned, I think, from the previous time, and I think he referred to that in this. I think basically what we are doing here is some kind of finite element analysis. This could be, in principle, also connected to his work by using such a basis in order to compute the, for example, other risk measures instead of the usual quadratic case. In fact, part of this was done in the thesis of my former student, Felipe Macias. Okay, I don't know how much time I have, actually. How much time I have? Huh?
20 minutes.
Oh, 20 minutes, but I was planning actually to finish way ahead of time. So I want to, since I'm rushing so much, you know why I gain so much time? Because I decided not to talk about the classical, well-known stuff. And I'm sure you're happy. Okay. So in order to check our algorithms, we started some textbook exercise. In fact, this is something that we programmed over one afternoon. It's very simple. You, for example, want to compute a call option, and you want to compute at the same time the hedging. You do a certain number of simulations. In this case, I even forgot how many simulations, 5,000 simulations. Perhaps I should read my slides before giving the talks. We used a small number of bases, a small sized basis. This was three elements. We managed to then compute the price. This is a comparison between the Black-Scholes price and the hedge Monte Carlo approach. The simulations were not done in the risk neutral measure. They were done in the historical measure. And the results with a very simple code agree very well. This is, for example, if you take the same thing and do, simultaneous, this is the hedging, the delta of the delta hedge strategy. Well, and I think this kind of simulation confirmed to me and convinced us that indeed we should go ahead and this algorithm had something special about it. Still on the side of textbook examples, take, for example, a Maghreb option with, let's say, 65 days between two assets, X1 and X2. Suppose that they satisfy your favorite model, for example, geometric Brownian motion. You go ahead and compute the Maghreb option by using the textbook formula. You actually get a very good relation between the prices and the hedge that you would obtain theoretically as with the computed one. So this is kind of textbook stuff, and we actually extended this extensively in the thesis of a former master student of ours, Milene Mondek, where we not only computed this for Brownian motion, but for several types of processes, Garch, and you name it, and then compare the, let's say, premium between one project, one price and another in cases where you don't have actual formula. So now let's talk about real practical examples. And this problem came to us in this project, this collaboration. So here we have an energy company that decides to consider the optionality of investing in a project that would last 11 years. The project is dependent on 12 different assets. The option is exercisable every year during the first 5 years. The company has a trading desk that could be used for the financial investment in some way or another. And we evaluate the project using several assets. The results that I'm going to report now were done using only one hedging variable, in this case the Brent price. We considered 2,000 pads along 11 years, and the interest rate was 8%. So over here in green, no, what color is that? Blue, yes, blue, I'm sorry. The pointer is green, yeah. in blue, you see the value of the real option, meaning the optionality to invest. And in red, you would see the value of the exercise, so the intrinsic value of the project, if it were immediately exercised. So what this is saying to us is that at this moment in time, this was at the beginning of this time, it would be better to wait instead of exercise, because you would be exchanging something that has more value than the actual value of the exercise. Here is an extension of this type of question. For example, consider a project that would run for 15 years, an investment of 1,500 monetary units, again 8% interest rate. And here what we're plotting is along those years the average cash flow distribution, just to give you an idea of what's going on, just to give us an idea of what was going on. Note that this is yearly, so it's very discrete. We're doing everything in discrete time. Note also that we are plotting here the lower and the upper quantiles, 90% quantile. So this is lower 5%, upper 5%. And so the simulations are all in the middle here. Okay? So description of these cash flows and the different scenarios is given here. From that, we can compute both the project value using the Hedge-Monte Carlo algorithm that I just mentioned, and we could compute the project option of investing in this project. And here again, these things are all computed for the different scenarios because we are using some kind of Monte Carlo simulation. So instead of putting all the paths there of this project value distribution, actually I'm just showing the quantiles, the lower 5%, the upper 5% quantiles, and the average. Okay, and here what I'm showing is the project intrinsic value distribution. Again, the upper and the lower quantiles, the average, and here we plotted using the algorithm the minimal initial intrinsic value, the minimal intrinsic value for exercise. So it has this kind of little bump here, and then it goes up a little bit, or it doesn't go up, but it kind of stabilizes a little bit. So from there, we can draw conclusions on what would be the best stopping time for different scenarios in different future times. And this could be used for many things at level of management, of course. A third practical example, this is actually a thought experiment. Since we're talking so much about Google today, we had the idea of, okay, let's consider a little Google car that runs on gas, and it gets cash flow if it's running around, and the better Google is doing, the more cash flow it gets. However, if the cost of running this car around since it's operated on gas, it's going to go up, the cost of running this car, or having this car running around. So we kind of imagine a cash flow that would be simple. This is just a thought experiment to have fun and to see how these things work. So it would be some kind of function that would be like, well, it's a function that starts at 0, then goes linearly up, and then is constant. And such function then would kind of model the fact that there would be a saturation above a certain point. It would be 0 if it's too small. And we've chose some constants A and B that would make sense. We added some extra non-hedgeable noise, and we simulated this, and we simulated the prices from real prices by calibrating the model for Henry Hub gas, for Google stock. And this is just to show you a histogram of such returns between August 2004 and 2013. Here are the simulations. And so these are the cash flows. Now, of course, you have many more simulations, but not so many more. We have nice quantiles. From there, we can get actually the project value. And from there, we can get the intrinsic, the minimum intrinsic value for exercise. We can also have the mean and the lower and upper quantiles. So this is a way of kind of taking an idea or getting an idea of how the project would go a long time. So I think this is a useful tool for this kind of project evaluation. Now, there are lots of questions, and questions of numerical type, questions of theoretical part. But let me conclude just by summing up what we have done. So, as I said, we implemented a real option pricing algorithm with code and, in a certain sense, available code for people who are interested in MATLAB and R. We also implemented this computation deferment option, which is the option, and the expansion option, which is an option over an option. So the deferment option is the usual real option everybody computes. The expansion is once you have decided to start a project, what is the value of an expansion over that project? So this is also implemented. The methodology is, in a certain sense, going the direction of model free, since we don't assume specific models for the cash flows, or we only use the cash flows that are provided to us. So if you are interested, there are more details in this paper. And now let me mention a few works that have been developed after the publication of that paper, in particular the PhD thesis of Felipe Macias that's under submission. The issue of calibration scenario generation is very important, and it's also part of the project that was being discussed yesterday by Juan Pablo Luna. Then the search for optimal base is a problem that I've been thinking about working on, but I have never really started. We started instead with Emmanuel Gobet and Gang Liu. Gang Liu is there. The questions on optimizing this computational process, and this is actually something that's very interesting. There are lots of theoretical problems related to this methodology as well, and I think this is a very fertile field. I just wanted to mention that this is a simulation, an example of simulation in this exercise, with this project that is ongoing with Gang and Emmanuel Gobet, Gang Liu and Emmanuel Gobet. So this is an example where we have very few simulations, and we can still, with very few simulations, get the price of a call option pretty close to the true price. So the issue here is that in these practical examples, we have few simulations, and we want to compute prices with few simulations. So in industry, they are not going to put a computer for us to work full-time or a cluster. So they are going to usually give us very few simulations, and we have to do our best with that. So this is the kind of thing that we are doing. I'd like to thank you for your attention, mention the collaborators. So Edgardo Brigatti is here, and I managed to get his picture. Max, you don't need to have his picture here. You can look at him in person. Felipe Macias, who is now working in Chile. Gang is hidden here by the Christ. And Emmanuel Gobet is our collaborator that I'm sure a good number of you know well. So I'd like to finish before Max, you might want to try to get Zubelli to announce a course that I'm going to teach. And this is for students, but anyone is welcome. Zubelli is not at IMPA anymore. I'm sorry. Okay, that's, well, yeah. Anyway, I missed my opportunity. My window of opportunity was missed. But anyway, I want to mention a course that I'm going to be teaching at the FGV starting January on math finance for practitioners. So if you have students around in Rio, especially people here from the community, the Brazilian community, I'm going to go very, very down to earth, and so it's a propaganda time. Sorry about that. It's going to happen at FGV Tuesdays and Wednesdays from 7 to 10 on weekdays during the period 5 January to 4th of February. So I'd like to thank you very much, and okay, I'm happy to be here. Sorry, very important, last but not least, I'd like to thank Rafaela for her wonderful work, and so please let's thank you, Rafaela.